Hello, everyone, and welcome to another Jakarta Tech Talk. My name is Serena, and joining us today is Thomas Langer, who will be presenting on the topic of use of virtual threads in Helidon. If you have any questions for Thomas as we move through today's presentation, feel free to ask them in the chat, or you can click on the Ask a Questions tab. Without any further delay, Thomas, over to you.
Thank you very much. Hello, everybody. Good morning and good afternoon, depending on where you are. I will talk a bit about virtual threads and specifically how we decided to use them in Project Helidon. I am architect of the project and I have been with it since its inception. So let's have a look at what Helidon is. Very short introduction. Helidon is a framework for developing Java microservices. The micro is intentionally in brackets. We can also build quite big services. It really depends on the choice of the developer. One of the main points here is that Helidon application is just a Java SE application. You run it using java-jar, which makes it very easy to containerize or to run locally and to play around with it. I will not dive very deep into it. I will just show a brief history of how we have worked on the project. We started in 2018, where we had a pre-1.0 version on Java 8, and we have moved through the Java versions up until today, where the active version is, actually there are two active versions, Java version 2, which is running on Java 11, and version 3, which is running on Java 17. And this year, with Java 21, we plan to release Helidon 4, which will actually be the topic of this presentation. Java 21 is very important for us, and the reason it is important for us is for these trade-offs that we have to solve when designing a services framework and when building applications. In most of the cases, when you build application using Java, you need to make this decision. Am I going to target ease of use, or am I going to target performance? There is not much possibility to cross these unless you dedicate a lot of time to designing everything and making sure your scalability is up to par with your requirements for performance. So for ease of use, you usually want to use a blocking paradigm because it's very easy to reason about and to code. You want to have wide library support. You need to have easy maintenance, and you need to have easy troubleshooting. But most commonly in Java, with these requirements, the performance suffers. So why does it suffer? In most cases, this is because of the limited number of threads that you can have in a Java application. Because the threads are a limited resource, a scarce resource, you need to allocate them correctly. And the problem with blocking code is that as long as you are blocking and waiting for somebody else to finish their task, such as a remote HTTP service, your thread is not allocated correctly. It's doing nothing, but it's still consuming resources. This can very easily lead to things like thread starvation, where you submit a task to an executor service to complete something asynchronously, but you wait for the task in your thread. And if you do this too many times in parallel, you may run out of threads to run your asynchronous tasks, and then you just stop working. So all of these things lead to a problem that if you have an application that requires heavily concurrent requests, such as an HTTP application, which is the usual use case, this approach is not very good. So how did we solve that? We solved it with the reactive paradigm. And reactive programming really allows us to utilize threads as much as possible. The side effect is that it is more complicated. There is a very steep learning curve. Troubleshooting and maintenance of these solutions are much harder. Even though we have a lot of good frameworks that help you with it, usually through reactive stream operators. For example, we have one in Helidon. There is one in most of the frameworks that support reactive programming. It's very easy to break it. So a lot of times when we get support requests, we will find out that somebody eventually decided to call that completable future.get within a reactive stream pipeline. And of course, that breaks the whole thing, because you block a thread. And as soon as you block a thread in reactive stream, you basically broke your server. So it's very hard to get right. You need to care a lot about exceptionally blocks. You need to take care of the future responses, creating what we used to call callback hell in JavaScript. We now have it in Java as well when you use reactive programming. It's very hard to do more than one task in parallel. So imagine you get a request, and then you need to split this request into 4 parallel tasks that execute, and then you need to join them back together and return something. In reactive programming, you need to be really an expert to be able to do something like that correctly. There are other pitfalls. For example, if you look at reactive streams, you will look at the flow interface in Java, where you have the publisher subscriber, and a lot of people tend to write their own subscribers. If you do that, you are kind of guaranteed to fail because that's a very tough interface to implement. So even though there are a lot of negatives to using reactive programming, we still support it because that's the only way how to write really performant applications in Java. And you can see that at the bottom, I have put the icons of our 2 flavors, what we call Helidon, and that's Helidon MP. MP stands for microprofile, and Helidon SE. And Helidon SE is right now, until version 3, fully reactive implementation. Helidon MP is on the other side, built on top of CDI, Jaxares, and it's foremost a blocking implementation. There are also some asynchronous things that you can do, but by default, you just build your application as a blocking application. And of course, you hit all the advantages and disadvantages of these 2 things. And we want to solve that. And luckily for us, Java came up with something called Project Loom. And Project Loom is a project to explore and incubate VM features and APIs for implementation of virtual threads. There are 3 JEBs for that. Virtual threads, which is a Java 21 GA feature right now. It's JEB 444. There is scoped values, which is a preview feature in Java 21. It used to be an incubator in Java 20 and before in Java 19. That's JEB 446. And there is structured concurrency. I still haven't seen the JEB for Java 21, but it was second incubator in Java 20. Obviously, for us, the most important one is the first one, because with Java 21, that should be a normal feature of the Java programming language, so we will not need to run with enable preview. I will talk a bit about each of them. So we will start with virtual threads, obviously. So what is a virtual thread? It's a thread that you can have a huge number of. You can have millions of them running in a JVM. It uses the thread API. It uses the fork join pool to schedule its work. All virtual threads are daemon threads. They always have a group called virtual threads, and they have no permission with a security manager. The existing threads that we know from Java language are now called platform threads. So what is the, how does it work? So virtual threads actually do use platform threads, and they do use them by mounting on the platform thread, which is called a carrier, to run some task. And when there is a blocking operation, they will unmount from it and do nothing. And the platform thread can continue running a different virtual thread for the duration of that wait. So there is an example here where we have some example where we call, let's call it an HTTP request that returns a completable feature. Now, up to this point, we are running on a carrier thread because virtual thread on its own cannot run. It needs to run on a carrier thread. When we hit this point where we call response future.get, the call is invoked, but the current thread stops being carried by the platform thread and is put aside, unmounted from it. When the completable future completes, and somebody on the other side of the equation calls completable future.complete or complete exceptionally, our thread will be revived. It will be mounted to a carrier thread again, and it will continue processing. And all of this is happening in the background. You don't need to know it. It just happens by the virtual machine. There are a few new APIs that allow us to work with virtual threads. Very important one is executors.new virtual thread per task executor, which will give you an executor service where every single thing that you submit to it will run on a new virtual thread. You can also check if a thread is virtual using the API. So all of this together allows us to build an application that is fully written as a blocking application, but at the same time doesn't need to care about the blocking points. So we no longer need to do reactive programming to be able to fully utilize our threads and to have high concurrency. We can actually use blocking code because as long as you are blocking, so for example, you invoke that SQL statement that takes 10 seconds to execute. So for those 10 seconds, you are not utilizing any platform thread at all. So other requests have access to them. Obviously, you can still overload such a system. You can always break stuff, but at least you no longer need to take care of the biggest problem of maintaining the number of threads according to the requirements of your application. The JVM will do that for you and make it easier. With every feature, there are some limitations. So let's look at the known limitations we have right now. So first one is there are several cases when the virtual thread cannot unmount from the platform thread. First are operating system level limitations. For example, file system operations are all blocking on the native level. And because of that, there is no way how to handle it. The Java team is working on some changes in this area because there are new APIs also written in Linux itself, which will allow us to also have asynchronous non-blocking file system operations, but it's not there yet. So when you use a file system, like you read a file, your platform thread will not be unmounted. Another limitations are coming from the JDK itself. For example, if you use object.wait, also your carrier thread will not be unmounted. These two operations are actually understood by the JVM, and Java will compensate it by temporarily increasing the number of threads in the for-join pool. So even though your thread is blocked, there will be a new one created because Java knows that this operation is not really needed for, or the thread is not that much needed for other operations, and it will resolve this problem as soon as you complete that operation. There is a second set of limitations, which are a bit worse, because these operations actually do hinder application scalability, because the carrier thread is pinned and the JVM will not create a new thread for you. And there are two cases, again. First one is a synchronized block. Now, synchronization is fine in Java as long as you do not do blocking operations within the synchronized block. So if you synchronize on a map, for example, either using the old hash table or using a synchronized map, you are probably not that much in trouble if you just create a new linked list as part of that operation. On the other hand, if you try to call a remote system within that synchronized block using HTTP, then you will probably break your application. So synchronized blocks do have some impact on virtual threads. Second part are native methods and foreign functions. So if you use native code from Java, Java cannot decide how to handle that. So unless that operation is fully implemented for virtual threads, the thread will become pinned. So for synchronize, there is a good solution. We can use the Java util locking mechanism, which is fully supporting virtual threads. For native methods, obviously, there is more work to be done. So if you are heavily depending on native methods, then maybe that is something that you need to wait until the library that you use resolves this problem. So that was the quick introduction into virtual threads. The second topic for Project Loom is structured concurrency. That will be very interesting when it comes out, because structured concurrency allows creation of structure within concurrent tasks. So if you want to, for example, create a task that spawns 5 subtasks, and you only care about all of them completing. And if one of them fails, you want the other ones to be canceled. Right now in Java, this is really hard to do. With structured concurrency, there is now a way to define policies, how you want to handle it. So if you start these subtasks, you can say, if one fails, I want all of them to fail. Or you want to say, I am just interested in the first one, I don't care about the other ones. And once you set it up, you will run your tasks. You can implement things like fork join, and eventually when the tasks are finished, you will get your result and you can continue. This is designed to match virtual threads. So when you run with structured concurrency, everything will work as you expect. Your thread will be blocked. It will be unmounted from the carrier thread. The asynchronous task will be executed, and the results will be correctly collected and returned back to you. What is really interesting about the support is that it's also supported in thread dumps. So once we use structured concurrency, when you do a thread dump, you will also see the structure of the tasks that were executed. Unfortunately, it's still a preview feature, so we cannot utilize it in the product in the GA version. But for the future, this will be very useful things. For example, in Helidon or other servers, you will be able to see all tasks that were spawned by a single socket, for example. So you will be able to really see it from the thread dump that, my admin socket has 25 tasks where it shouldn't have any. The class that you want to look at is structured task scope. So if you want to play around with it, Javadoc will probably guide you, and there are resources on the net. Very interesting feature of Project Loom. The next and the last feature that is right now available in Java is scope values. Again, it's still a preview feature, unfortunately, because scope features are kind of a replacement for thread locals. Scope values allow you to share immutable data across threads. Why is it important? Because thread locals allow you to set and unset the value as you want. So if you have access to a thread local, you can just change the value. And when the value is, for example, a security context, then maybe unsetting is not exactly what you want people to do. And scope values work in a way that you set the value and then you run the subtasks with that value set in stone. And then it's removed when you finish. And this is, I'm actually reading the next slide here. So the lifetime ends when you finish your task. Again, with thread locals, when you set a thread local on a platform thread, it will stay there forever or until you call remove. And to be honest, remove is not being called properly by most developers. So you will have a lot of things associated with a thread that probably shouldn't be associated with it. So this is what scope values are fixing. Also inheritance, it's very expensive to copy thread locals to child threads. With scope value, this is actually designed and works nicely. And we have to understand that with virtual threads, we need to start counting in thousands and hundreds of thousands of threads. So these things need to be really well designed. Otherwise, you will run out of memory or you may have some performance impacts. And thread locals are exactly that. They are a performance impact to any application that wants to fully utilize virtual threads, because you obviously need to synchronize on a thread local. So based on all these features that we have seen are coming to Java, we have decided with the first preview version in Java 19 to look what we could do in Helidon about it. And what we came up with is what we call Helidon Níma. And that's the first framework that is based on virtual threads. And when I say based on virtual threads, it's actually built from the grounds up and designed for virtual threads. Another typo. What we wanted to do is to achieve performance of reactive programming with the simplicity of blocking code. And as I always say on these talks, our benchmark is what Netty is capable of. We are using Netty in Helidon 1, 2, and 3, and we know it's a performant web server, and we wanted to see if we can achieve similar performance using virtual threads and properly blocking code. And because we found out that this is achievable, we actually came up with Níma, and the Níma web server is the new core of Helidon. So how do we utilize virtual threads? When you use HTTP 1.1, it's quite simple. There is just a single virtual thread per connection. And this virtual thread is responsible for reading data from the connection, invoking your route, and then writing response data. We have some ways how to tweak it. For example, you can have an asynchronous write for HTTP 1.1 connections, where you will actually have two virtual threads, one reading the data, one writing them for optimizations. It works on some systems, it doesn't on others. On the other hand, HTTP 2 is actually very interesting because that really utilizes the power of virtual threads. You have one virtual thread per connection, which is handling the maintenance of the connection, because in HTTP2, there is one connection and you have packets that are running around, and each of them returns to one stream, and the stream is basically your request response HTTP interaction. So each of these streams also runs a single virtual thread. What that means is that whenever you have a route in HTTP on Helidon, it will be executed within a virtual thread. And that in turn means that you will be able to block as desired. So this is the main thing that we have with Helidon 4.0. We will be running on virtual threads, and we will be utilizing them from the core of the web server. I will talk a bit about the things that we have learned during that. I will just show a quick peek into our performance measurements. So the smaller number, the dark one, is the number that we could see on Helidon SE. So this is actually our micro-profile application, and the first one is running on top of Netty and our SE core, and the light blue is on top of our own Níma web server. And we can see there is quite a huge improvement. And the question would be like, why do we get so much when we already had a reactive server before? And the reason is that first, we don't need to tune the number of threads that are available for our MP application. And the defaults are usually not sufficient if you have a very high load. And second thing is that with the blocking code and Níma, everything is much more simple. We could actually remove probably more than half of the code that was responsible for integration with the reactive streams and with Netty, and that actually resulted in much better performance. Okay, so that was introduction and how we use it in Helidon, and now I will talk about the lessons that we learned with virtual threads, and most of them are advantages that are applicable to any application. So for me, the biggest lesson learned was you actually need to unlearn asynchronous programming. With all the problems that we had in enterprise applications in the past decades, when you wanted to do anything fast, you always ended up doing something asynchronously. And now we don't need to do that. And honestly, it's hard to tell yourself that you don't need to do it. But once you unlearn that, you will find out that everything is easier to write, it is easier to read, and it is easier to maintain. If you have a try-catch block, it will work as a try-catch block. You don't need to look for some future exception that may come when something is returned from a completable future. There are some things that we will have to wait. Some libraries may need to catch up. When I wrote this slide, actually, Oracle JDBC driver, for example, was not supporting virtual threads. But now I can say that it's already fixed because we trust in this feature, and Oracle has already released JDBC drivers that do support virtual threads. But there may be other libraries. You need to check with the library vendor if it is going to hinder performance with virtual threads. In most cases, it shouldn't, because there are only very limited use cases where you actually can get into trouble, but it's kind of good to understand that. Obviously, you need to look at synchronized code in your application to make sure that you don't do something that would break the performance. I talked about it before, especially when you have any kind of blocking code that is executed within a synchronized block that needs to be refactored to locks. You should think about thread locals. Use them not that much. Try to remove them as much as possible. There are obviously cases where there is no way around it, but we have found out that it's not that big problem to use a couple. It's a problem if you use too many. And for me, virtual threads are the best improvement in Java ever. And I'm working with Java since version 1.1. And honestly, this is like the best thing that ever happened to it. So let's go to lessons learned 2. Simplicity brings performance. So first, we switched from non-blocking channels to blocking sockets. And this was something that was unintuitive for me at the time, that actually removing non-blocking and using just simple socket and SSL socket improved performance. As a side effect, SSL is way easier than to using SSL engine with non-blocking channels. We found out that buffer reuse is detrimental to performance. There is a trade-off, obviously. If you use new buffers for every read on every socket, you will be polluting your memory a bit. But because all of these buffers are extremely short-lived, we have found out that the JVM has no problem garbage collecting it very fast. And we didn't see any performance impact of this part. On the other hand, when we try to reuse buffers, with all the virtual threads that you have, it's actually costing you time and CPU. So it is better not to reuse them. And again, relearn to use blocking. It is much easier for everything. We have found out something that is a bit unfortunate. There are a few performance-sensitive things that depend on the operating system. And one of those I already talked about, it's asynchronous writes. TCP no delay, or the Nagel algorithm, sometimes it's faster, sometimes it's not. If you use Mac OS, it works just fine with TCP no delay and synchronous writes. If you use the latest Linux kernel, you will find out that it's not so good. If you use an older Linux kernel, it works the same as on Mac OS. So there is like a bunch of things that are happening. So if you want to achieve top performance and you have requirements of, let's say, hundreds of thousands to millions requests per second on your system, you will need to do proper due diligence on your environment. And you should not upgrade your Linux kernel blindly. You should first make sure that there is no performance impact. And this is not really a performance impact on Helidon side, it is on the socket level of JVM. I think that this will improve over time. This is a new feature, so we need to understand that there will be some time where maybe there will be bigger impacts of these things. It still works. You may just need to do some fine tuning. Again, HTTP 2. I was surprised that HTTP 2 is quite complicated. It's much harder to read for humans what is happening on the network. On the other hand, it's the best thing for virtual threads. So I would recommend to use HTTP 2. It really is the right way forward because you utilize your connections better. You don't need to have 10 connections from a single client just because you are running 10 things in parallel. You can use a single connection and run it all on that single one. We also have gRPC implementation of HTTP 2, which again was much easier than we expected. So now, because of that, we can handle multiple protocols on the same port. So we can have HTTP 1, HTTP 2, gRPC, WebSocket, all handled on the same protocol. For example, in Helidon 3, if you want to run gRPC, you need to run it as a separate server because we use the netted gRPC, which cannot be combined with the rest of Helidon. And one of the targets that we set is to actually remove all dependencies on native from Helidon. So the only server that will be in Helidon will be Helidon Níma. Now, last thing I have a slide for is one thing that we don't solve. And this cannot be solved with virtual threads, and it can be solved in reactive as well, and that's obstruction of a thread. And we get this question quite often, like, so how do you solve the problem when a thread wants to run a long-term task that is fully utilizing it and is using yields? And my answer will be, well, you do it the same way that you did it in reactive. You run it on a different executor service, and you wait until it finishes. So with reactive, you would probably have some completable future where you would say, then accept and do your task. Well, in virtual threads and in Helidon, you would just have call get on that completable future, and your virtual thread will be blocked, and that asynchronous obstructing task can run the way that you intended it to run. So very simple solution. The only difference is that you just don't react, you block, you wait until it is done. And this is always everywhere in blocking code with virtual threads. You run something and you wait until it finishes. You don't need to do any asynchronous tasks within your HTTP endpoint. You just do .get on your futures, and that's it. And of course, with structured concurrency, it will be even easier because you will have support for it in the operating system. In the JVM. Okay, so I have a very short example in the source code. So let me quickly switch to that. On the left, I have code that is written for Helidon Níma, and on the right, I have code that is written for Helidon Reactive. And we can see that as long as you do a very simple task, like in this case, I'm just calling a remote client, and I'm getting the string entity from it, and then I'm sending it back. It looks very similar. Like you get your request, you get a future of a string. Single is just like a completable future in Helidon. And then on that response, you say, okay, for single, which is similar to then accept for completable future, just send it over the response. And if there is an exception, send that exception using the response. And this will do an internal server error. With Helidon 4, it's blocking. So you say, I want to get my remote string entity. You just get it. You don't get a future, you get that entity. And I say, oh, I want to send it over the response, and I'm done. I don't care about exceptions. If an exception happens, it will be taken care of by the system, and you will get that appropriate internal server error, or maybe that exception will be mapped correctly to an error handler that you have registered with the server. But where it becomes more interesting is in the complex cases. So let's say I want to use the status code that was returned by the remote side, and I want to set it on the response. And in blocking world, I submit my request, I get a response, and then I set the status, and I send the response. And if I wanted to send the entity, I could just say, client response. And here I could do, for example, something with that entity. I could do a string, or I could get an input stream and do whatever I want. Blocking coding, you don't need to do anything complicated. You do the same thing in reactive programming. Suddenly need to expand your lambdas, and here in the correct place, you will say, oh, here I get my response, I can do something. But if you wanted to do something with the publisher, it will be actually much more complicated. And now imagine that here, when you get the response, you would like to do 2 tasks in parallel, and then depending on the response, you will need to do something. And I can tell you, I did that code. We actually implemented it. I spent probably 1 hour trying to troubleshoot it and make sure that everything works correctly, and it is really done asynchronously, because it's not a simple task. if I did it in blocking code, I know my executor.submit and how to handle that and how to wait for the futures. So really, my world is much simpler now. I don't have a problem with writing code for synchronous. I do always have a problem writing code for reactive, and I can tell you, I'm not the only one. Our customers that use reactive have problems as well. They use it because there is no other choice. So now, what we like to declare, we kind of hope reactive is dead, and virtual threads will take over and make our performant applications easier to write and easier to use. Okay, with that, thanks for the attention, and I'm now free to answer any questions if you have any. I don't see anything in the chat, so feel free to ask.
Hi, Thomas. Yes, so there's actually Andrub is asking if you could share the slides.
Yes. How can I share them?
So we'll ask for the. Did you want to potentially provide an email address where people can send you a quick email?
I think that's okay. I'll just share it here in the chat.
That's perfect. There you go, Andrub. If there's any questions that you have and requests, just send it over to Thomas directly, and he will be able to send you the slides. And that goes for anyone else as well that has any further questions or would like to reach out to Thomas. So I wanted to say thank you for the excellent presentation today, Thomas. And as a reminder, before we wrap things up, but for everyone in the audience to ask the questions in the tab, but also to let you know that Jakarta Tech Talks happen on a monthly basis, a couple of times a month. Throughout the entire year. And so we are looking for more presenters for the end of the year. So if you are interested, kindly fill out the form that I'm going to link into the chat. And of course, if you have any feedback on the Tech Talk programs, we would love to hear from you. So once we end the broadcast, just click on the green button that pops up and let us know how we can improve it. So I think that is it. It says we got another question here, Thomas, from George. Did you hit out of memory errors? You answered that.
So I actually didn't manage to kill my server with out of memory. I think that on my machine, I was running the limits of the client itself. And I didn't try to restrict memory. So I'm running with 32 gigs of memory on the testing machine. I was able to reach 1 million requests per second. I know that one of my colleagues was running a bigger test where he managed to hit around 3.5 million requests per second with HTTP2. And the problem that he hit was that the client started disconnecting, but he didn't get an out of memory error. And I think that one of the reasons is that the out of memory, you would really need to fill your memory with all the HTTP headers that are coming in. And because the lifetime of a single request is quite short, the garbage collector has enough time to clean it up. So I'm sure you could run out of memory. If you build an application that will read everything from the request and then sleep for 10 seconds and then return it, and then you hit it with 1 million requests, you will probably run out of memory. But that is it's not a new thing. The same thing happens in reactive. The same thing happens if you have a blocking application. If you have too many in-progress requests, you will run out of memory. But you always have an option to control how many requests you have in memory. I think that there are a lot of problems that didn't disappear. You will still need to take care of performance. We will hit different bottlenecks than we used to hit. So, for example, in the old applications, usually your database was one of the biggest bottlenecks, and your threads were the second biggest bottleneck. With virtual threads, database will stay. There is no difference unless the database is come up with a solution to better utilization of HTTP or sockets to handle multiple requests, they will probably be the bottleneck still. And memory, of course, will become the next bottleneck when you have a lot of requests, because you will be able to load your services with higher load. I hope that answers that question.
Perfect. It does. Yeah, that's great. Anything else from anyone else? Give it a couple seconds. All right. Well, thank you again, and you all have yourselves a wonderful day. Take care, everyone.
Thank you. Bye-bye.
Bye.